13.8 billion years ago, the universe began. In one moment, there was nothing, and the next, there was everything. Just how this is possible is perhaps the biggest question in all of science, crossing the boundaries between theory and experiment, physics and philosophy. Everything we know about our universe hinges on mechanism, process, and causality. We strive to understand the reasons things are the way they are. And yet, at the most fundamental level, we do not know how or why the entire universe came to be. But this lack of explanation is not for want of searching. Perhaps, as famed cosmologist Stephen Hawking once supposed, there really was nothing before. Considering space and time as inherent, conjoined properties of the universe we inhabit, the beginning of that universe marked the beginning of time. Before time, there could be no space, and therefore no universe. Considering the geometry of space-time, back through the ages, it contracts, curves around, and eventually rounds out. Searching for something beyond that would be as meaningless as searching for something that was north of the Earth's North Pole. Or perhaps there was no actual beginning, but rather a limit to our powers of observation. Scientists believe that it was a split-second period of exponential expansion, known as inflation, that put the bang in the Big Bang and set the stage for everything that was to follow. Our inflation stopped after a tiny fraction of a second, but some physicists have argued that this is not the only period of inflation in the cosmos as a whole. Rather, inflation continues elsewhere eternally, producing bubble universes distributed through a potent, everlasting multiverse. Or perhaps our current universe is merely the latest in a long and potentially infinite series of expanding and contracting cosmos, a theory known as the Big Bounce. In this, instead of starting from nothing and inflating exponentially to produce the structure we see today, contemporary physicists suggest a cyclical growth and contraction of everything within the universe. Or perhaps our understanding of scale is fundamentally incomplete. One physicist considered the properties of shapes, regardless of their size, and believes we can do the same with the cosmos. In this idea, the universe loses a sense of time and scale at the infinitely small and the infinitely big and becomes, to all intents and purposes, equivalent. The game of chess is played the same whether on a board that fits in your pocket or spans an entire courtyard. Or perhaps our cosmos came about as a transient collision of dimensions. Superstring theory attempts to explain the fundamentals of reality as tiny vibrating strings within an 11-dimensional reality of hyperspace. The 3 dimensions of space and 1 dimension of time that we experience within our cosmos are merely a single brain in the overall bulk, with the beginning and growth of our universe coming about as higher-order brains collide. Or perhaps there is something else, some corner of mathematics or physics that we have yet to shine a light into and which, for the time being, eludes our understanding. For now, our universe's origin story remains a mystery, a multiple-choice, choose-your-own adventure. Nevertheless, 13.8 billion years ago, the universe did begin. This is the story of what happened next. Even if we traveled at more than 50,000 kilometers an hour, it would still take more than 80,000 years to arrive at Proxima Centauri, our closest star. It is estimated there are 100 billion more distant stars in the Milky Way. Indeed, sometimes it can be overwhelming to square our own lives with the vastness of everything else. And to work these things through, it's nice to have some help. The world's largest therapy service, which is 100% online, offers a network of over 30,000 licensed and experienced therapists who can help with a wide range of issues. You can talk to your therapist however you feel comfortable, whether it's via text, chat, phone, or video call. You can message your therapist at any time and schedule live sessions when it's convenient for you. If your therapist isn't the right fit for any reason, you can switch to a new therapist at no additional charge. With this service, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who is custom-picked for you, with more scheduling flexibility and at a more affordable price. Get 10% off your first month at the provided link, which is also included in the description below. Thanks to this service for supporting educational content. Where is the hottest place in the universe? You might expect to find it in the natural fusion reactor at the center of a star. But even as you incinerate in the plunge through its fiery depths, your journey would be in vain. Temperatures at the core reach a mere 15 million degrees Celsius. You may look to even more violent phenomena in the cosmos, like explosive supernovae. Here, during the dramatic death of a star, superheated shells of gas are ejected many light years in every direction, leaving a gravitationally compactified neutron star at their center. Temperatures here far exceed normal stellar furnaces, reaching 100 billion degrees Celsius, but this still isn't the hottest temperature to be found. In fact, the highest temperature that has ever been recorded anywhere in our vast cosmos was 100 meters beneath the snow-covered ground near the shores of Lake Leman in Switzerland. And it didn't come about from a natural process, but rather the concerted efforts of hundreds of scientists and billions of euros worth of research and development. In the Large Hadron Collider, where individual particles are routinely smashed into one another at velocities approaching the speed of light. The collision of two lead atoms in 2012 briefly produced a temperature of around 5.5 trillion degrees Celsius, 50 times hotter than a supernova. But this still isn't even close to the highest possible temperature. Temperature is little more than a manifestation of a particle's energy, its motion, or how fast it is vibrating. Absolute zero, marking 0 Kelvin, equivalent to negative 273.15 degrees Celsius, is the lowermost limit, where particles hypothetically would come to a complete shuddering stop, were it possible to reach. But there is also an upper limit too, an absolute hot, that marks the highest temperature before the particles themselves are torn apart by their own energy. It's known as the Planck temperature, and it is around 1.4 times 10 to the 32nd Kelvin. Max Planck, who gave his name to this impossibly blistering temperature, was a dedicated German theoretical physicist who found his academic stride around the beginning of the 20th century. His ideas are seen as the founding blocks of quantum physics and led to the quantization of light into discrete chunks of energy called photons. But they also led him to consider the fundamental quanta of other natural phenomena, using such universal qualities as the speed of light and the force of gravity in combination with his eponymous Planck constant that he derived from his work on electromagnetic radiation. He defined the Planck length, the smallest quantum of distance, as around 1.6 times 10 to the minus 35 meters, around 100 quintillion times smaller than a proton. The time it takes for light to travel this minuscule distance through a vacuum is the Planck time. amounting to 5.39 times 10 to the minus 44 seconds. And the Planck temperature, that a practical measure of absolute heat, is the temperature at which the wavelength of thermal radiation reaches the Planck diameter. It can go no smaller. It is no fair reflection on the human brain to say that these numbers are beyond our true comprehension. We are evolutionarily attuned to scales that are relevant to us, and so it may seem that these Planck units are too small, or in the case of temperature, too large, to be of any practical use. But it is when contemplating the immeasurably tiny moment at the beginning of our immeasurably vast cosmos that these units really come into their own, because our universe is expanding, becoming less dense, and has been for all of its history. Scientists don't know if our universe is infinite or not, but if it is, then it always has been. So rather than starting as a single point, it would also have begun infinitely large, and rather than grow over time, it would simply have become less dense. Our observable universe, however, is different. It is the only part of the universe we could ever see, or interact with, or could ever see and interact with us, and is limited by the speed of light and the distance it has been able to travel since the universe's birth 13.8 billion years ago. But as we travel back in time, that observable part of the universe shrinks and becomes more compact, until eventually we get to a time when everything within it was only a single Planck unit of time old, a single Planck length in diameter, and with all of our observable universe compacted into such a tiny space, the temperature of the whole cosmos sat squarely at Planck temperatures. It may come as little surprise to learn that this moment, 100 million trillion trillionths of a second after the beginning of time and space, is known as the Planck era. And it is a very strange time. In the cosmos today, everything we experience is governed by certain immutable laws of nature, which are ultimately controlled by the interaction of four major forces: the strong force holding atoms together, the weak force governing certain types of radioactivity, the electromagnetic force distributing energy over great distances, and gravity. As Max Planck predicted at the end of the 19th century, the strong, weak, and electromagnetic forces can be quantized, represented, and thought of as tiny and indivisible parcels of interaction, kind of like particles of matter. These so-called messenger particles are known respectively as gluons, W and Z bosons, and photons. But gravity is different. With his general theory of relativity, Albert Einstein was responsible for overthrowing the classical mechanical definition of gravity. Instead, he conceptualized it as the curvature of space-time, a warping in the very fabric of reality. Through various large-scale experiments, general relativity has been verified time and time again, and the gravity-induced curvature of space-time is now recognized as a property inherent to the universe, which affects all matter and energy within it. Therefore, during the Planck era, long before any of the conventional laws of nature held sway, it was gravity that was first to manifest. But there is a problem. Everything we know about the workings of gravity today is based on Einstein's successful theory, but that theory is only really tested and verified on larger scales. During the Planck era, however, our entire observable universe was condensed into an area many trillion times smaller than a proton, and general relativity simply does not help. Instead, the dynamics of the extremely tiny are governed by quantum mechanics. At scales small enough that we can consider the individual subatomic particles of matter, or the quantized messenger particles of force and energy. An entirely different set of rules holds sway, where nothing is ever where you expect it to be, and the very act of observing changes the outcome. Instead of dealing in absolutes, quantum physicists consider probabilities, and nothing ever stays the same for long. Fortunately for us, this lawless quantum world only reigns on nanoscopic scales, and by the time we reach magnitudes that we're more familiar with, the probabilistic weirdness averages out. But during the universally nanoscopic Planck era, there is no escaping the quantum. And herein lies the problem for understanding how things actually worked in that moment. General relativity and quantum mechanics are fundamentally incompatible with one another. So researchers are still searching for a solution, a so-called quantum gravity, that is able to reconcile two of the most important theories in modern physics and properly describe how the Planck-era universe behaved. Unfortunately, it is a question that cannot reasonably be tackled by experimental means. Considering the vast energies needed to produce and study the other force messenger particles inside collider facilities, and the elevated plane that gravity occupies in defining all of space-time, it would take a particle accelerator roughly the diameter of our entire solar system to generate enough power to truly probe gravity during the extremes of the Planck era. But this doesn't stand in the way of theoretical speculation and extrapolation. One idea suggests that, like the other fundamental forces of nature, gravity also is communicated by a messenger particle, a quantum unity of gravity that has come to be known as a graviton. But gravity as a force is so much weaker than the others that its meager messenger would be practically impossible to detect. Another theory, known as loop quantum gravity, is very different. In this, physicists imagine the smooth and ever-changing geometry of space-time to be ultimately pixelated on the very smallest scales, and by rewriting Einstein's equations of general relativity in terms of lines or loops instead of points, the calculations for gravity on a quantum scale become much more manageable. And perhaps the leading possible quantum gravity solution continues to rumble away in the background of theoretical physics. String theory imagines the point-like particles of traditional physics as one-dimensional, vibrating strings, and it is the vibrational state of the strings that defines what a particle is, as well as the elusive force of gravity. And yet, in order to make the mathematics of string theory work, it becomes necessary to involve no fewer than 10 or 11 dimensions, many of which are folded in on themselves within the strings themselves, or are partitioned into 2 or 5-dimensional structures known as branes, the fundamental objects of an even more elusive overarching theory with the simple moniker M. Each of these hypotheses for how quantum gravity may actually work is more mind-bending than the last, rooted in the abstractions of mathematics, almost impossible to visualize. And yet that is just what we are trying to do when we cast our minds back to imagine the first fraction of a second of our universe during the Planck era. Ironically, it was in the 1950s, when the science of quantum mechanics was still in its infancy, that a theoretical physicist provided us with a tangible description of conditions in that turbulent and confusing time. The early universe was imagined to be composed of a bubbling and dynamic quantum foam. This quantum foam, as described, comes about because of the dynamical and unpredictable nature of interactions on the quantum scale. The uncertainty principle seriously compromises our ability to define length, time, or energy at any one point within the Planck-sized universe, and so the continuous and coherent space-time that we are familiar with today is replaced by an inherently unpredictable and varying foam-like texture that shifts and changes randomly. Quantum micro-black holes and wormholes spring spontaneously into existence and then disappear without a trace, without any apparent cause and effect. In this highly energetic, super-compact, and miniaturized cosmos, for the briefest of moments, anything goes. But after only 100 million trillionths of a second, the widespread unpredictability of the Planck era comes to an end as the gradual and minuscule growth and cooling of the universe heralds a new epoch. The universe won't look or behave anything like it does today for a while. But from here on out, our current theories do at least stand a chance of describing what is going on. Everything in our universe is controlled and defined by the four fundamental forces of nature. Imagine turning on your television. Gravity keeps you pinned firmly to the seat of your chair, holds the Earth's atmosphere close to the surface, and holds the Earth in orbit around our nearest star, providing a habitable environment for your continued existence. Yet despite this, gravity is relatively weak, and you can overcome it with the muscles of a single arm. To lift the remote. In response to your button press, invisible infrared light, electromagnetic radiation beams across the living room from the front of the remote. The picture comes to life in front of you. Through millions of tiny pixels emitting visible light, another form of electromagnetic radiation which travels back across the room and into your eyes. Your eyeballs themselves are marvels of evolutionary innovation, but they ultimately rely on the properties and behaviors of the atoms within. Electrons and nuclei held together by the electromagnetic force. The atomic nuclei themselves are held together by the strong nuclear force. Protons and neutrons forced together in the center of the atom. Not only that, these protons and neutrons are really a combination of three smaller subatomic particles, called quarks, which are also bonded by the same pull. Every atom in your body, in the television, in existence itself, relies upon this force. As your eyes focus and you engage with the pictures moving on the screen in front of you, each of the nerves inside your brain fire at up to 200 times per second. All of that coordinated electrical potential relies on a proper balance of potassium in the body. Like the other elements, potassium is held together by the strong nuclear force, but there is something else at play as well. Because potassium is very slightly radioactive, and around 5,000 potassium atoms radioactively decay every second, a decay driven by the weak nuclear force. And 150 million kilometers away, the core of our sun burns with the heat of a stellar furnace, powered by the fusion of hydrogen into helium. This incredibly powerful reaction is responsible for the heat that keeps the Earth habitable, and on a galactic scale, the very elements that make up the planet, the television, and you. And all of this is also reliant on the weak nuclear force. It may be weak in name, but it is mighty in its reach. Each of these four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, act together to shape our experiences of the universe. And so it has been for the majority of our cosmos's multi-billion-year history. But in the very first moments of time, conditions conspired to craft a very different set of rules, derived from the same basic physical ingredients. During the Grand Unification epoch, which followed the Planck era, there were only two forces. But how could this be the case? The key to visualizing this lies in a coin toss. Flip a coin to decide between two equally weighted choices, heads for one team, tails for the other. The decision is only reached when the coin settles after the flip, when the energy provided by the flexing of thumb and forefinger is completely spent, and the disc comes to rest. Before that point, when the coin is still imbued with energy and it is spinning through the air or across the table, it is nigh on impossible to even distinguish its two faces, the two choices available to you. There is just a single spinning orb, with characteristics all of its own. This is what we encounter when we examine the behaviors of the fundamental forces at higher energies, the energies that were present in the nascent universe. Increase the temperature dramatically, and the individual properties of the weak nuclear force and the electromagnetic force begin to weaken and blur into one another. We no longer see the distinct heads of electromagnetism and the tails of the weak force, but rather the spinning, faceless force of the two united, the so-called electro-weak force. Increase that energy even further, and the spinning coin concept again applies to the strong force and the electro-weak. With high enough temperatures, these two blur into a single unified whole in a process known as grand unification. This ultimate unification of three of the major fundamental forces gives rise to what is known as the electro-strong force. Though this tidy spinning coin theory of grand unification has yet to be definitively proven experimentally. Even though the energetic collisions inside particle accelerators can point us towards the joining of electromagnetism and the weak force, it would take energies some million times greater for the strong force to lose its identity in the same way. Even the most energetic phenomena in the universe today, like supernovas and the jets emitted from the poles of black holes, are still 1,000,000 times too feeble. And as for whether gravity, the fourth fundamental force, is ever accepted into the unified fold, that is a question for the mysterious and unpredictable Planck era, and yet another problem for contending theories of quantum gravity to address. Still, the grand unification theory, as it is known, is a strong contender for explaining the workings of the universe just after the Planck era. For a period of time, some 10 million times longer than the entire Planck era, the universe expanded and cooled. But it is testament to just how small everything started out, that even by the end of this time, the entire cosmos was still smaller than a single quark, the smallest particle of matter known today. With the latent energy of that cosmos compressed into such a tiny space, the temperature reached 100 billion trillion Kelvin, some trillion times higher than the Large Hadron Collider has ever managed. These were the conditions for the grand unification epoch, ruled by the chimeric electro-strong force and the bizarre interactions that it brings about. The minuscule cosmos is filled with particles undergoing an extreme identity crisis. Photons transform spontaneously into matter-antimatter pairs, creating quarks and leptons. But these nascent particles are desperately short-lived, decaying rapidly back into photons scarcely as soon as they have formed. Electro-strong messenger bosons only serve to complicate the picture, helping quarks to transform into leptons, leptons into quarks, matter into antimatter, and vice versa. Under the chaotic rule of grand unification, it is a free-for-all of energy and matter, of particles both virtual and real. Until a trillionth of a second after it began, the penny drops. Temperatures drop to a mere 1,000 trillion degrees, rendering it cool enough for the strong force to break free. for two forces to become three, and everything changes once again. And yet, there is a problem with this picture. While these theories may adequately describe the behavior of particles within the earliest moments after the Big Bang, they fall short of explaining the large-scale cosmos that will eventually come to exist. When comparing the starting conditions with a universal end result, the Big Bang appears to be broken. By July 2022, the iconic James Webb Space Telescope was well established in orbit around the Sun, 1.5 million kilometers out in space. Following a nail-biting month-long journey and a phase of deployment and calibration that lasted almost a year, it was finally ready to begin its scientific operations in earnest. But when it focused its 18 golden mirrors into some of the deepest reaches of the observable universe, scientists were shocked. After seeing the images return from the revolutionary telescope, an astrophysicist wrote in the scientific journal Nature that she found herself lying awake at 3 in the morning, wondering if everything she had ever done was wrong. Within a month, these images and her comments had grown a life of their own. The fixed speed of light means that the deeper we peer into space, the farther back in time we are looking, and at distances corresponding to just 200 million years after the beginning of everything, the James Webb Telescope had seen galaxies. Not only that, but these galaxies were ordered with much more structure than anyone had thought possible. Theories of star and galaxy formation had no way to explain it, and it was this that the astrophysicist had been so concerned about. Unfortunately, soon her concerns had been extrapolated to cast doubt on the Big Bang, with some media outlets claiming that the next-generation telescope had disproved the landmark theory with its very first images. Thankfully, those concerns were misplaced. The astrophysicist had only been concerned about existing theories on galaxy formation, not entire cosmos creation. The inexplicable structuring of early galaxies meant that there was a piece missing from our understanding. Not that everything we knew was wrong, little more than a storm in a cosmic teacup. And so, the Big Bang is safe from that quarter, for now at least. But as a complete explanation of how our modern universe